and aerodynamic considerations. We will begin by discussing the high-altitude environment, including airspace definitions, limitations, and oxygen requirements. We will review high-altitude weather, including the jet stream and its effect on turbulence. Then we will discuss the physiological effects of pressure, including decompression and high cabin altitudes. We will conclude the lesson by examining aerodynamic considerations during high-altitude maneuvers. High-altitude flight can be considered starting when the aircraft enters Class A airspace, which includes all airspace from 18,000 feet MSL up to flight level 600. In the United States, 18,000 feet MSL also represents the transition altitude. Below the transition altitude, altitude is referenced in feet. Above this, altitude is referred to as flight levels. Aircraft operating above the transition altitude use a standard pressure reference of 29.92 inches of mercury or 1013.2 hectopascals regardless of the actual sea level pressure. Regulations for operating at high altitude specify the oxygen requirements for flight crew members. These requirements are based on aircraft altitude and cabin pressure altitude. First, we'll review the oxygen requirements based on US 14 Code of Federal Regulations, Part 91. If operating within an unpressurized cabin, the flight crew must use supplemental oxygen when the cabin pressure altitude exceeds certain thresholds. Specifically, oxygen must be used at cabin pressure altitudes greater than 12,500 feet up to and including 14,000 feet if the time at those altitudes exceeds 30 minutes. When the cabin pressure altitude exceeds 14,000 feet, both flight crew members must use oxygen at all times. When operating a pressurized cabin aircraft at flight altitudes above flight level 250, at least a 10-minute supply of supplemental oxygen is required for each flight crew member and passenger on board. If one pilot leaves the flight deck and the aircraft is operating above flight level 350, the remaining flight crew member must don and use their oxygen mask until the other pilot returns. If the aircraft is not equipped with quick donning type masks, at least one crew member must use supplemental oxygen at flight altitudes above flight level 350, even when both pilots are present. Federal aviation regulations for operating at high altitudes also specify the oxygen requirements for other cabin crew members and passengers. Part 91 specifies that at cabin pressure altitudes above 15,000 feet, each occupant on board must be provided with supplemental oxygen. Under Part 121 regulations, an emergency oxygen supply is required for each passenger. This oxygen is required to be available when operating above 10,000 feet. Passenger oxygen is typically supplied by the chemical oxygen generators located in the passenger service units, or PSUs. During an emergency, the PSUs will open, either automatically or under manual control, and individual oxygen masks drop from the ceiling. Pulling on the oxygen mask initiates a chemical reaction which produces oxygen. Aircraft operate in multiple layers of the Earth's atmosphere, including the troposphere, tropopause, and stratosphere. Aircraft normally operate in the troposphere, which extends from ground level to approximately 35,000 feet around the poles and up to 65,000 feet around the equator. The temperature in the troposphere decreases with altitude at a rate of approximately 2 degrees Celsius per 1,000 feet. The troposphere also contains roughly 80% of the Earth's atmosphere. The tropopause is a thin layer which acts as a boundary between the troposphere and the stratosphere. In the tropopause, the air temperature ceases to cool with altitude and the air contains very little moisture. Above the tropopause is the stratosphere, which extends to an altitude of approximately 22 miles. The stratosphere is characterized by a relatively constant temperature of -55 degrees Celsius with little moisture. This layer also tends to remain stable with very little turbulence. Earth's atmosphere consists of approximately 78% nitrogen, 21% oxygen, and 1% other gases. These ratios do not change with altitude even though air density decreases. For example, at 18,000 feet, air density is approximately 50% less than at sea level. However, the ratio of oxygen to other gases is still 21%. Jet streams are a narrow band of relatively strong winds near the tropopause. These winds typically travel in an easterly direction at speeds of 50 to 200 knots. The two strongest jet streams are the polar jets and the subtropical jets. These jets typically move in a meandering path and even merge at times. The subtropical jet stream is typically located below 30 degrees latitude, while the polar jet is typically located between 30 to 60 degrees latitude. Because of the higher wind velocities, the possibility of clear air turbulence exists at high altitudes. Clear air turbulence is defined as turbulence where no clouds are present, and while it can occur at any altitude, it tends to develop near the jet stream. Typically, clear air turbulence tends to be stronger on the polar side of the jet stream and is more pronounced during winter months. In addition to the turbulence caused by the jet stream, turbulence can also develop as a result of mountain waves, low pressure aloft, or high altitude wind shear. Clouds located at high altitudes are usually composed of ice crystals. Cirrus and cirrostratus clouds are found in the stable air above 30,000 feet and typically result in little or no turbulence. Clouds with extensive vertical development, such as cumulus and cumulonimbus clouds, are indicative of very unstable air which contains moderate to heavy turbulence and icing. These clouds typically start in the lower altitudes but can easily reach heights of 60,000 feet or more. Care should be taken to circumnavigate cumulonimbus clouds whenever possible. Icing at high altitudes does not typically present as great of a problem as it does in the lower altitudes. This is because low moisture content and low temperatures result in slow ice accumulation. Icing at high altitude typically occurs in tall cumulus buildups, anvils, and over mountainous regions. To ensure the safe outcome of a pressurization emergency at high altitudes, it is important to understand the physiological effects of reduced air pressure and oxygen depletion. Your body uses hemoglobin to transport oxygen from the lungs to body tissues. The amount of oxygen carried by hemoglobin varies with the partial pressure of oxygen in the atmosphere. As a result, the human body functions normally from sea level to approximately 12,000 feet. Above 12,000 feet, the atmosphere contains significantly less partial pressure of oxygen and can result in such problems as hypoxia and decompression sickness. In general, hypoxia can be defined as a lack of sufficient oxygen in the body's cells or tissues. This can be caused by an inadequate supply of oxygen, inadequate transportation of oxygen, or the inability of the body to use oxygen. For flight at high altitudes, it is important to understand the symptoms of hypoxia. These symptoms vary between individuals, but one of the earliest effects of hypoxia is impaired judgment. Other symptoms include behavioral changes, poor coordination, discoloration at the fingernail beds known as cyanosis, sweating, increased breathing rate, headache, sleepiness or fatigue, loss or deterioration of vision, lightheadedness or dizzy sensations and listlessness, and tingling or warm sensations. Hypoxia can be broken down into four main groups: hypoxic hypoxia, histotoxic hypoxia, hypemic hypoxia, and stagnant hypoxia. Hypoxic hypoxia is caused by an insufficient partial pressure of oxygen as a result of the reduced atmospheric pressure at altitude. If you recognize the onset of hypoxic symptoms, the immediate use of supplemental oxygen will alleviate the symptoms very quickly. For this main reason, it's important that the oxygen systems be checked prior to takeoff to ensure they are functioning properly. If at any time supplemental oxygen is not available, a descent to an altitude below 10,000 feet should be initiated. Histotoxic hypoxia is caused by the inability of the body cells to use oxygen because of impaired cellular respiration. Typically, this type of hypoxia is caused by alcohol or drug use. Supplemental oxygen is ineffective because oxygen intake is impaired at the tissue level. The only way to avoid this type of hypoxia is to abstain from using alcohol or drugs prior to a flight. Hypemic hypoxia is defined as a reduction in the oxygen carrying capacity of the blood. Typically, this is caused by a reduction in circulating red blood cells or the contamination of the blood with gases other than oxygen. Some of the causes of hypemic hypoxia may include anemia, carbon monoxide poisoning, or excessive smoking. Smokers are far more susceptible to hypoxia at lower altitudes than a non-smoker. For example, a heavy smoker's oxygen carrying capacity at sea level is equivalent to a non-smoker's capacity at 7,000 feet. At 20,000 feet, the equivalent altitude for a smoker would be approximately 22,000 feet. Stagnant hypoxia is caused by an oxygen deficiency in the body resulting from poor blood circulation. This type of hypoxia is usually the result of coronary artery disease. This type of hypoxia can also be caused by prolonged exposure to extended G-forces or positive pressure breathing. The amount of time a person with an insufficient supply of oxygen is able to perform flight duties is known as their time of useful consciousness. This is also referred to as effective performance time, or EPT. Even though the altitude at which hypoxia affects a pilot varies, their EPT will always decrease with altitude. At 30,000 feet, the EPT is 30 to 60 seconds. At 40,000 feet, the flight crew has only 7 to 10 seconds to take corrective action. A malfunctioning pressurization system or structural damage to the aircraft can result in uncontrolled decompression. Decompression can be categorized in 3 levels: gradual, rapid, and explosive. Gradual decompression occurs slowly and in some cases may go unnoticed. Most aircraft have pressurization warning systems to alert the flight crew of gradual decompression. The symptoms may include eardrum and sinus pressure changes. Rapid decompression typically takes more than 1/2 second, but less than about 10 seconds. There is not the high potential for lung damage, however debris and fogging will be present in varying degrees of severity. Any decompression that takes place in less than 1/2 second is considered to be an explosive decompression. In comparison to rapid decompression, the risk of lung trauma or rupture during an explosive decompression is very high. This is due to decompression occurring at a rate faster than it takes for air to escape from the lungs. Debris and fogging will also be more severe during explosive decompression. In all cases, decompression may result in hypoxia, and a descent to an altitude below 10,000 feet should be initiated. Most of the effects of decompression are a result of either trapped gases or evolved gas disorders. The effects of trapped gases are a result of Boyle's law, which states that the volume of any gas is inversely proportional to the pressure exerted on that gas. So, any gas trapped in the human body will expand with a drop in the pressure surrounding the body. This can occur in many parts of the body, causing varying degrees of discomfort or pain. Examples of this include ear blocks, sinus block, dental problems, and intestinal problems. Evolved gas disorders are more commonly referred to as decompression sickness or DCS. This effect is commonly observed when the top is removed from a carbonated beverage, causing a release of pressure and forcing the carbon dioxide to bubble out of the solution. The same thing that happens to the human body. When nitrogen has been dissolved in the blood and other body tissues at a high atmospheric pressure, for example at sea level, transitioning to a lower pressure will allow the nitrogen to come out of solution in small bubbles. Gases coming out of solution in the body can affect the circulatory system, the chest and lungs, more commonly referred to as the chokes, the muscles and bones, more commonly referred to as the bends, and the nervous system. Be aware that scuba diving before flying tends to compound this problem. Therefore, it's important to wait at least 12 hours after a non-compression stop dive, or 24 hours for a dive with decompression stops, for any flights where the cabin pressure altitude will exceed 8,000 feet. Prolonged oxygen use can also be harmful to human health. 100% aviation oxygen can produce toxic symptoms if used for extended periods of time. The symptoms can consist of bronchial cough, fever, vomiting, nervousness, irregular heartbeat, and lowered energy. These symptoms appeared on the second day of breathing 90% oxygen during controlled experiments. It is unlikely that oxygen would be used long enough to produce the most severe of these symptoms in any aviation incidents. However, prolonged flights at high altitudes using a high concentration of oxygen can produce some symptoms of oxygen poisoning, such as infection or bronchial irritation. The sudden supply of pure oxygen following a decompression can often aggravate the symptoms of hypoxia. Therefore, oxygen should be taken gradually, particularly when the body is already suffering from lack of oxygen. If symptoms of oxygen poisoning develop, high concentrations of oxygen should be avoided until the symptoms completely disappear. To cope with high-altitude environments, it is essential to have a good understanding of high-altitude aerodynamics. Understanding high-altitude aerodynamics begins with understanding basic aerodynamic principles such as the total drag curve. The total drag curve divides flight into two categories which are defined by the lowest point on the curve, known as the LD max. Speed faster than LD max is considered normal flight, or the front side of the drag curve. When operating with a constant thrust setting, any airspeed disturbance will result in the airspeed eventually returning to the original airspeed. The speed range slower than LD max is known as slow flight, which is also referred to as the backside of the drag curve, or the region of reverse command. When operating with a constant thrust setting, any disturbance causing a decrease in airspeed will result in a further decrease in airspeed unless thrust is increased. This principle becomes more important as aircraft are pushed to more efficient flight profiles to save fuel, resulting in high-altitude cruising at lower Mach numbers. In this situation, the crew may have less time to recognize and respond to factors causing airspeed decay, resulting in flight slower than LD max. Under normal circumstances at lower altitudes, recovery from this situation requires an increase in thrust to power out of the condition, with emphasis on minimum loss of altitude. However, while at high altitudes, there may be an inadequate amount of thrust available to return to speeds above LD max. Trying to maintain altitude with insufficient thrust will result in a further reduction in airspeed. Instead of trying to maintain altitude, a descent will be necessary in order to prevent further airspeed decay and the potential for a stall. Mach speed is the ratio of the aircraft's true airspeed relative to the speed of sound. When the aircraft's true airspeed reaches the speed of sound, it is referred to as Mach 1. Typically, Mach airspeed is thought of as affecting the aircraft as a whole. However, accelerated air over parts of the aircraft can reach supersonic speeds, even though the aircraft itself may be flying subsonic. The speed of an aircraft at which airflow over any part of the structure first reaches Mach 1 is termed the critical Mach number. When the critical Mach number is reached, shock waves begin to form at the area of supersonic flow. As airspeed increases, the shock wave begins to move aft. At speeds 5 to 10% above the critical Mach number, these shock waves begin to have a major effect on the aircraft and drag begins to increase rapidly. Associated with this rapid drag increase are buffet, trim and stability changes, and a decrease in control surface effectiveness. These effects are referred to as Mach buffet. Mach buffet will continue to increase with increased speed and the aft movement of the shock wave. The shock wave also causes the wing's center of pressure to move aft, resulting in a pitch down tendency known as Mach tuck. To avoid speeds above the critical Mach number, you should reference your VMO/MMO speed. VMO is the aircraft maximum operating speed. This is a fixed value and is valid up to a fixed altitude determined by the aircraft manufacturer. This altitude, referred to as the crossover altitude, is the altitude at which a specified calibrated airspeed and Mach value represent the same true airspeed. Above this altitude, the Mach maximum operating speed, or MMO, is used. MMO is a fixed Mach value, but since Mach speed is relative to the speed of sound, the corresponding maximum airspeed is reduced at higher altitudes. Optimum altitude is defined as the best cruise altitude for a given weight and air temperature. In other words, optimum altitude is the cruise altitude for minimum cost when operating in the econ mode and for minimum fuel burn when in the long-range cruise or pilot-selected speed modes. This altitude is not constant and will change over the period of a long flight as conditions and the weight of the aircraft change. For example, a dramatic increase in temperature will lower the optimum altitude, while a decrease in aircraft weight will increase the optimum altitude. Therefore, when flying at optimum altitude, crew should be aware of changes to both aircraft weight and environmental conditions. Maximum altitude is the highest altitude at which an airplane can be operated. It is the lowest of maximum certified altitude, thrust limited altitude, or Buffett limited altitude. Maximum certified altitude is a structural limitation that is determined during certification and is usually set by the pressurization load limits on the fuselage. Thrust-limited altitude is the altitude at which sufficient thrust is available to provide a specific minimum rate of climb. Thrust-limited altitude is affected by temperature. As temperature increases, the thrust-limited altitude will decrease significantly. Most jet transport airplanes are thrust-limited, which is why it is imperative that crews be aware of outside temperature and available thrust. Buffet limited altitude is the altitude at which a narrow maneuver margin exists prior to buffet onset. There are two kinds of buffet to consider in flight: low-speed buffet and high-speed buffet. As altitude increases, the indicated airspeed at which low-speed buffet occurs increases, while the high-speed buffet speed decreases. This is referred to as absolute ceiling or coffin corner. At this ceiling, a reduction in airspeed results in exceeding the stalling angle of attack, resulting in low-speed buffet. An increase in speed results in exceeding MMO, potentially leading to high-speed buffet. Although these limits are monitored by modern flight management computers, the available thrust may limit the ability to accomplish anything other than relatively minor maneuvering. The danger in operating near these limits is the potential for the speed and angle of attack to change due to turbulence or environmental factors, leading to a slowdown or stall and subsequent high-altitude upset. High-altitude operations have a significant effect on aircraft controllability. Normally, there is an adequate maneuver margin at optimum altitude. As the aircraft approaches maximum altitude, maneuver margin decreases significantly due to insufficient thrust. In modern aircraft, the use of LNAV ensures bank angle is limited to respect buffet and thrust margins. Other automation modes or hand flying may result in excessive bank angles. At higher altitudes, this may result in drag exceeding the normal maximum cruise thrust limit. If this occurs, using maximum continuous thrust may provide enough thrust to maintain your current bank angle. However, the safest course of action is to stay well below the aircraft's maximum altitude. Weight and balance can have a negative impact on aircraft controllability, particularly with an aft center of gravity. The further aft an aircraft is loaded, the less effort is required by the tail to counteract the nose-down pitching movement of the wing. The less effort required by the tail results in less induced drag on the entire aircraft, resulting in the most efficient flight. For efficiency purposes, aft loading is relatively common. However, aft loading makes the aircraft less stable and can severely affect stall recovery. These issues will also be exacerbated at high altitudes. Moving the CG forward improves longitudinal stability but may result in less efficient flight. Most aircraft that fly at high altitudes are built with swept wings, as this design delays the adverse effects of flying at high Mach speeds. Sweepback theory is based upon the concept that only the component of the airflow perpendicular to the leading edge of the wing affects pressure distribution and the formation of shock waves. Simply put, the airflow relating to the formulation of shock waves is being reduced. This allows for higher true airspeeds to be attained before critical Mach is reached. While a swept wing is more efficient at high altitudes and airspeeds, it does have some negative side effects. One side effect is an increase in stall speed. In the event of a stall, the wingtips of a swept wing tend to stall first, which reduces aircraft control along the roll axis. Due to lack of stability, swept-wing aircraft also have a greater problem handling Dutch roll and adverse yaw. In addition, the lower air density at the aircraft's maximum ceiling results in a higher true airspeed but a lower indicated airspeed. Consequently, this can increase the probability of encountering Dutch roll and adverse yaw. Dutch roll is both a roll and yaw oscillation that occurs when roll stability is reduced in comparison to yaw stability. If the problem is not corrected, the oscillations tend to increase, compromising aircraft stability. Adverse yaw is a yaw tendency in the opposite direction of a turn. The likelihood of encountering these stability issues in modern aircraft has been greatly reduced by the use of yaw damper systems.